Stegosaurus is a genus of herbivorous, four-legged armored dinosaur from the Late Jurassic, characterized by the distinctive kite-shaped upright plates along their backs and spikes on their tails. Fossils of the genus have been found in the western United States and in Portugal, where they are found in Kimmeridgian and Tithonian-aged strata, dating to between 155 and 145 million years ago. In the Upper Morrison Formation of the western United States, only 3 Stegosaurus species are universally recognized: Stegosaurus stenops, Stegosaurus ungulatus, and Stegosaurus sulcatus. Fossils from over 80 individual Stegosaurus have also been discovered. Stegosaurus would have lived alongside dinosaurs such as Apatosaurus, Diplodocus, Camarasaurus, and Allosaurus, the latter of which may have preyed on it. They were large, heavily built herbivorous quadrupeds with rounded backs, short forelimbs, long hind limbs, and tails held high in the air. Stegosaurus is one of the most recognizable dinosaurs, distinguished by its broad, upright plates and tail tipped with spikes. The function of this array of plates and spikes has been the subject of much speculation among scientists. Today, it is generally agreed that their spiked tails were most likely used for defense against predators, while their plates may have been used primarily for display and secondarily for thermoregulatory functions. Stegosaurus had a relatively low brain-to-body mass ratio and a short neck with a small head, indicating it likely fed on low-lying bushes and shrubs. Among its species, Stegosaurus ungulatus is one of the largest known stegosaurians, with the largest specimens reaching approximately 7.5 meters or 25 feet in length and weighing over 5 tons. Stegosaurus remains were first identified by Othniel Charles Marsh during the Bone Wars, a Dinosaur Ridge National Landmark. The initial skeletons were fragmentary and scattered, leading to years of uncertainty about the dinosaur's true appearance, including its posture and plate arrangement. Despite its popularity in books and films, Stegosaurus did not become a staple in major natural history museums until the mid-20th century. Many museums have had to create composite displays from several different specimens due to the scarcity of complete skeletons. Stegosaurus, a quadrupedal dinosaur genus, is easily recognized by its distinct features. A double row of kite-shaped plates rising vertically along its rounded back, paired with 2 sets of long spikes extending horizontally near the tail's end. Stegosaurus stenops reached 6.5 meters or 21.3 feet in length and 3.5 tons in body mass, while Stegosaurus ungulatus reached 7 meters or 23 feet in length and 3.8 tons in body mass. Some large individuals may have reached 7.5 meters or 25 feet in length and 5 to 5.3 tons in mass. Most of our knowledge about Stegosaurus derives from the remains of adult specimens. However, more recently, juvenile fossils of Stegosaurus have been uncovered. One subadult specimen, unearthed in Wyoming in 1994, measures 4.6 meters or 15.1 feet in length and stands 2 meters or 6.6 feet tall. It is estimated to have weighed between 1.5 to 2.2 tons during its lifetime and is currently exhibited at the University of Wyoming Geological Museum. Stegosaurus and related genera were herbivores, but their teeth and jaws were very different from those of other plant-eating ornithischian dinosaurs, suggesting a unique feeding strategy that is not yet well understood. Other ornithischians had teeth designed for grinding plant material and jaws capable of various movements. In contrast, Stegosaurus had small peg-shaped teeth with horizontal wear facets, indicating tooth-food contact, and their jaws likely moved only up and down. Their teeth were not tightly packed for efficient grinding, and there is no evidence that they used gastroliths, stones ingested to help grind food. As a result, how Stegosaurus managed to obtain and process the large amount of plant material needed to sustain its size remains poorly understood. Stegosaurians were widely distributed geographically during the Late Jurassic period. Paleontologists believe they ate plants such as mosses, ferns, horsetails, cycads, and conifers. One theory suggests they were low-level browsers, feeding on plants up to 1 meter above the ground. However, if Stegosaurus could raise itself on its hind legs, as suggested by Bakker, it might have been able to browse vegetation as high as 6 meters or 20 feet off the ground. In 2010, a detailed computer analysis of Stegosaurus's feeding behavior used 3D models of its teeth and realistic physics. The study calculated bite forces of 140.1 newtons, 183.7 newtons, and 275 newtons for the anterior, middle, and posterior teeth respectively, which is less than half that of a Labrador retriever. This suggests Stegosaurus could easily bite through smaller green branches, but struggled with anything over 12 millimeters in diameter, indicating it primarily fed on smaller twigs and foliage. However, a 2016 study found that Stegosaurus's bite strength was stronger than previously thought. By comparing a specimen known as Sophie with 2 other herbivorous dinosaurs, the study revealed that Stegosaurus had a bite strength similar to modern herbivorous mammals like cattle and sheep. This suggests it likely ate tougher, woodier plants, such as cycads, possibly helping to spread cycad seeds. Stegosaurus typically had 17 dorsal vertebrae, each with elongated centra, the main body of the vertebra, and elevated dorsal transverse processes, bony projections. These adaptations provided attachment points for muscles and ligaments, supporting the dinosaur's large body. The ribs attached to these vertebrae, forming a sturdy rib cage that protected the vital organs. The forelimbs of Stegosaurus were shorter and less robust compared to its hind limbs, giving the dinosaur an unusual posture. The scapula, or shoulder blade, was subrectangular with a robust blade, but the coracoid was subcircular, contributing to the dinosaur's overall mobility and strength in its upper body. The hind limbs were powerful and supported most of the dinosaur's weight, allowing for efficient movement. The skull of the Stegosaurus was elongated and narrow, relatively small compared to its body size. It featured a small antorbital fenestra, a characteristic hole between the nose and eye found in most archosaurs, including modern birds, but absent in living crocodilians. The skull's low position suggests that Stegosaurus likely fed on low-growing vegetation. This hypothesis is supported by the absence of front teeth, which were probably replaced by a horny beak. The lower jaw had flat extensions both downward and upward, completely concealing the teeth when viewed from the side. These extensions likely supported a turtle-like beak during the dinosaur's life. The presence of such a beak along much of the jaws may have prevented the development of cheeks in these species. This extensive beak adaptation was likely unique to Stegosaurus and some advanced stegosaurids among ornithischians, which typically only had beaks at the tips of their jaws. Some researchers interpret these jaw structures as modified versions of similar features in other ornithischians, potentially supporting fleshy cheeks rather than beaks. Stegosaurian teeth were small, triangular, and flat, with wear facets indicating they ground their food. Despite its considerable size, the brain case of Stegosaurus was relatively small, comparable in size to that of a dog. In the 1880s, Othniel Marsh utilized a well-preserved Stegosaurus brain case to create a cast of the brain cavity, or endocast, providing insight into the animal's brain size. The endocast revealed that the brain was exceptionally small, proportionally the smallest among all known dinosaur endocasts at that time. The fact that an animal weighing over 4.5 tons could have a brain of no more than 80 grams contributed to the popular old idea that all dinosaurs were unintelligent, an idea now largely rejected. Actual brain anatomy in Stegosaurus is poorly known, but the brain itself was small even for a dinosaur. Initially, Marsh speculated that Stegosaurus might have been bipedal due to its short forelimbs, but in 1891 he concluded it was quadrupedal, considering its robust build. There has been debate over whether Stegosaurus could rear up on its hind legs to reach higher foliage, using its tail for support, proposed by Bakker, but opposed by Carpenter. Mallison's study in 2010 supported a rearing posture in related species like Kentrosaurus, but not with the tail acting as a tripod. Stegosaurus had noticeably shorter forelimbs compared to its hind limbs, with the lower section of the hind limbs, tibia and fibula, relatively short compared to the femur. This anatomy suggests it was not a fast walker, with a maximum estimated speed of 15.3 to 17.9 km per hour, or 9.5 to 11.1 miles per hour. Fossilized tracks indicate that Stegosaurus lived in herds of mixed ages, as observed in tracks showing juveniles and adults moving together. Due to the hindrance posed by its plates during copulation, it is speculated that female Stegosaurus may have laid on her side while the male mounted from above and behind. Another hypothesis suggests the female could have squatted on all fours, lowering her forelimbs while raising her tail to allow the male access. However, there is no evidence of mobile penises or bacula penis bones in male dinosaurs, suggesting their reproductive anatomy differed from modern reptiles and mammals. If it weren't for its pointed, symmetrical, vaguely threatening-looking plates, Stegosaurus would be a completely unremarkable dinosaur, a bland, small-brained, second-tier plant eater like Iguanodon. Fortunately, for its place in the popular imagination, though, the late Jurassic Stegosaurus possessed one of the most distinctive doos in the animal kingdom. These double rows of tough, bony, roughly triangular plates that lined this dinosaur's back and neck. Stegosaurus's plates were giant-sized versions of the osteoderms, protrusions of bony skin that are found on modern crocodiles, and may, or may not, have been covered in a layer of sensitive skin. Crucially, the plates of Stegosaurus weren't directly attached to this dinosaur's backbone, but rather to its thick epidermis, which afforded them more flexibility and a wider range of motion. So, what was the function of Stegosaurus's plates? There are a few current theories. One hypothesis suggests that plates of Stegosaurus were a sexually selected characteristic, similar to the tail of a male peacock, where males with bigger, pointier plates may have been more attractive to females during mating season, or vice versa. However, there is currently no evidence supporting variation in the size of Stegosaurus plates among individuals or between sexes. The plates served as a temperature regulation mechanism. If Stegosaurus was indeed cold-blooded, like most herbivorous dinosaurs of the Mesozoic era, it likely used its plates to absorb sunlight during the day and release excess body heat at night. A study in 1986 found dense networks of blood vessels in the outer layers of Stegosaurus's plates, providing evidence for this hypothesis. The plates increased the apparent size of Stegosaurus to meat-eating dinosaurs like Allosaurus, which likely had limited vision. Adults with larger plates would have been less appealing to predators, potentially leading to the survival and reproduction of individuals with this trait across generations. This may have been an especially important consideration for newborns and juveniles, as an adult Stegosaurus would have been quite a mouthful with or without plates. The plates had a defensive role, despite being loosely attached to Stegosaurus's skin. When the dinosaur tilted sideways during an attack, the sharp edges of the plates would angle towards its attacker, potentially deterring it from pursuing further. This theory, proposed by paleontologist Robert Bakker, is not widely supported among scientists. The plates were covered by a thin membrane of skin and could change color, possibly turning bright pink or red. This blushing in Stegosaurus might have served a sexual function, or it could have been used to communicate with other herd members about potential threats or nearby food sources. The high level of blood vessels in the plates, as mentioned earlier in relation to temperature regulation, lends further support to this idea. The arrangement of Stegosaurus plates has been a major topic in books and articles, and a significant debate in the history of dinosaur reconstruction. Over the years, 4 possible plate arrangements have been proposed. Flat along the back. Initially, Othniel Marsh believed that the plates lay flat like shingles on a roof, leading to the name roof lizard. However, as more complete plates were discovered, it became evident they stood on edge rather than lying flat. Single row of plates. By 1891, Marsh suggested a single row of plates. This idea was quickly abandoned, likely due to misunderstandings about how the plates are embedded in the skin and concerns about them overlapping too much. However, it was revived in the 1980s by Stephen Cherkas, who based this arrangement on the dorsal spine of iguanas. Paired plates. Charles Knight's 1901 reconstruction and the 1933 film King Kong depicted the plates paired in a double row along the back. Alternating plates. By the early 1960s, the idea of two alternating rows of plates became prevalent. This arrangement remains the most accepted today, largely due to partially articulated fossils of Stegosaurus stenops that support this configuration. This alternating arrangement is chiral, meaning each specimen can be distinguished from its hypothetical mirror image form. Thagomizer, tail spikes. There has been debate about whether the tail spikes were only used for display, as posited by Gilmore in 1914, or used as a weapon. Robert Bakker noted the tail was likely to have been much more flexible than that of other dinosaurs, as it lacked ossified tendons, thus lending credence to the idea of the tail as a weapon. Stegosaurus could maneuver its rear effectively by stabilizing its large hind limbs and using its powerful but short forelimbs to pivot swiftly in response to threats. Recent research by McWhinney, focusing on tail spikes, revealed a high incidence of trauma-related damage, supporting the idea that the spikes were used in combat. It was found that 9.8% of examined Stegosaurus specimens had injuries to their tail spikes. Further evidence includes a punctured tail vertebra of an Allosaurus, perfectly fitting a tail spike, with bone remodeling indicating infection and healing. Stegosaurus stenops possessed 4 dermal spikes, each measuring about 60 to 90 centimeters, or 2 to 3 feet long. Articulated stegosaur armor discoveries indicate that in some species, these spikes protruded horizontally from the tail, contrary to the vertical depiction often seen. Initially, Marsh described Stegosaurus ungulatus with 8 tail spikes, different from Stegosaurus stenops, but recent research has re-examined this, concluding that both species likely had 4 spikes. Juveniles of Stegosaurus have been preserved, probably showing the growth of the genus. The 2 juveniles are both relatively small, with the smaller individual being 1.5 meters or 4.9 feet long, and the larger having a length of 2.6 meters or 8.5 feet. The specimens can be identified as not mature because they lack the fusion of the scapula and coracoid and the lower hind limbs. Also, the pelvic region of the specimens are similar to Kentrosaurus juveniles. One 2009 study of Stegosaurus specimens of various sizes found that the plates and spikes had slower histological growth than the skeleton, at least until the dinosaur reached its mature size. A 2013 study found that Kentrosaurus had a faster growth rate than Stegosaurus, as indicated by the rapid deposition of highly vascularized fibrolaminar bone. This finding contradicts the general rule that larger dinosaurs grew faster than smaller ones. In 2022, a study by Weiman and colleagues examined various dinosaur genera, including Stegosaurus, and suggested that Stegosaurus had an ectothermic or cold-blooded or gigantothermic metabolism, similar to modern reptiles. This conclusion was based on analyzing certain chemical signals that are linked to metabolism. The researchers suggested that many ornithecian dinosaurs, including Stegosaurus, likely had a cold-blooded metabolism. They also proposed that these dinosaurs evolved from warm-blooded ancestors. At one time, stegosaurs were described as having a second brain in their hips. Soon after describing Stegosaurus, Marsh noted a large canal in the hip region of the spinal cord, which could have accommodated a structure up to 20 times larger than the famously small brain. This has led to the influential idea that dinosaurs like Stegosaurus had a second brain in the tail, which may have been responsible for controlling reflexes in the rear portion of the body. This brain was proposed to have given a Stegosaurus a temporary boost when it was under threat from predators. However, this space likely served other purposes. The sacrolumbar expansion is not unique to stegosaurs or even ornithecians. It is also present in birds. In birds, this expansion contains a structure called the glycogen body, whose exact function is unknown. It is thought to supply glycogen to the nervous system, act as a balance organ, or serve as a reservoir of compounds that support the nervous system. Kentrosaurus, a stegosaurid dinosaur genus discovered in the early 20th century, lived in the Late Jurassic period. It is notable for its distinctive body structure, a smaller version of the more famous Stegosaurus, with a double row of spikes and plates along its back and tail. Kentrosaurus' story begins during German expeditions to what was then German East Africa, now Tanzania, between 1909 and 1912. These expeditions unearthed hundreds of bones in the Tendaguru Formation, a site rich in Jurassic-era fossils. Edwin Hennig, a German paleontologist, first described the type species Kentrosaurus aethiopithecus in 1915, formally introducing Kentrosaurus to the world. Kentrosaurus, a smaller member of the Stegosauridae family, reached approximately 4.5 meters or 14.7 feet in length and weighed around 1,000 kilograms or 2,200 pounds. Kentrosaurus had a robust body structure characterized by straight hind limbs that differed from its more flexible forelimbs. Interestingly, Kentrosaurus exhibits potential signs of sexual dimorphism, differences in physical appearance between sexes, particularly in the variation of femur bones. Some bones appear more robust than others, suggesting differences between males and females, either in size or perhaps in mating behavior. Kentrosaurus had an elongated skull with a herbivorous beak and likely fed on low-lying vegetation. It may have also used a tripodal stance, standing on its hind limbs with support from its tail to reach higher vegetation beyond the reach of a typical quadrupedal stance, indicating its flexibility and strength in these areas. Central to Kentrosaurus' physical description is its defensive armor. Starting from the neck, a series of small bony plates ran along the dinosaur's back, gradually giving way to longer, sharper spikes as they progressed towards the tail. The culmination of this defensive feature was the Thagomizer at the end of the tail, which would have been a menace to any predator. A double row of these spikes and plates differentiates Kentrosaurus from the rest of the stegosaur family. This arrangement would have allowed a higher degree of flexibility and control over its tail, allowing for effective defensive measures. Wuerhosaurus. Wuerhosaurus is an extinct genus of stegosaurid dinosaur from the early Cretaceous period of China. As such, it was one of the last genera of stegosaurians known to have existed, since most others lived in the late Jurassic. Wuerhosaurus was unique that way. Two species have been discovered, which were called Wuerhosaurus homini and Wuerhosaurus ordocensis. Wuerhosaurus homini likely had a broad body, with estimates by Gregory Scott Paul in 2010 suggesting a length of 7 meters or 23 feet, and a weight of 4 tons. Due to the scarcity of bones, reconstructing its full appearance has been challenging. Initially thought to have rounder or flatter dorsal plates, later research by Maidment revealed this to be an illusion caused by breakage, leaving the true shape unknown. A reminder of the many mysteries in dinosaur research. The pelvis of Wuerhosaurus homini featured strongly flared front ilia, indicating a broad belly, and it had exceptionally tall neural spines on the base of its tail. In contrast, Wuerhosaurus ordocensis, estimated at 5 meters or 16.5 feet long and 1.2 tons by Paul, possessed a broad pelvis but shorter neural spines. Its relatively long neck resembled its cousin Dacentrurus. The tail thagomizers of Wuerhosaurus resembled those of its larger North American relative Stegosaurus and other late Jurassic to early Cretaceous stegosaurs. Wuerhosaurus adapted to feed on low-growing vegetation by staying close to the ground, unlike most other stegosaurids. Like its relatives, it possessed a thagomizer on its tail, akin to Stegosaurus, equipped with 4 bony spikes likely used for defense. Despite the discovery of only a single spike positioned near the shoulder, Wuerhosaurus stands out as one of the last stegosaurians, enduring through global extinctions and demonstrating remarkable evolutionary resilience. Dacentrurus was a member of the Stegosauridae group, a family of dinosaurs known for their distinctive plated backs and spiked tails. These herbivores are a testament to the incredible biodiversity that existed during the Late Jurassic to early Cretaceous periods, approximately 155 to 125 million years ago. The Dacentrurus, with its robust build and defensive armor, offers a glimpse into the survival strategies of dinosaurs during this period. Dacentrurus derives its name from Greek roots, da meaning very or full of, kentron meaning point, and ora meaning tail. This evokes an image of a dinosaur with a tail adorned with spikes, highlighting its defensive capabilities, a crucial element of its survival strategy. Along with Stegosaurus, Dacentrurus was one of the largest species of stegosaur, with some specimens estimated to have reached 7.9 to 9.1 meters, or 26 to 30 feet in length, 1.8 meters or 5.9 feet in hip height, and 550 kilograms, or 1,210 pounds in body mass. For a stegosaur, its gut was especially broad, and its exceptionally wide dorsal vertebrae centra indicated a massive rump. The hind limb was rather short, but the forelimb relatively long, largely because of a long lower arm. One of the most notable specimens of Dacentrurus is the holotype specimen, which was discovered in the late 19th century. This specimen includes a nearly complete left forelimb, a series of vertebrae, and several other elements. The preservation of these elements has allowed scientists to gain valuable insights into the anatomy and lifestyle of Dacentrurus. For instance, the long lower arm suggests that Dacentrurus may have been capable of rearing up on its hind legs, perhaps to reach higher vegetation or to defend itself against predators. While their social behavior remains uncertain, the presence of multiple individuals at some fossil sites suggests that Dacentrurus may have lived in herds or family groups. However, more evidence is needed to confirm this. Regardless of its social behavior, Dacentrurus had a significant presence in its environment due to its large size, distinctive armor, and likely profound impact on the vegetation and landscape through its feeding habits.